Okay, welcome to the second part of this video. We're going to continue on talking about Fnet and then some of the Newton's laws which dictate how forces and motion are related. So the concept of Fnet is that a lot of times, almost all the time, there's more than one force acting on an object. And so in order to figure out the overall effect of those forces, you need to add them up as vectors. So that means you take into consideration both the magnitude, which is how large the force is, but also the direction. So if two forces are both pointing the same way, they're going to reinforce each other and be an even larger overall force. But if you have one force, say, forward and one force backwards, they're going to partially cancel out, and the overall force will be the difference between the two. So when we're looking at just one dimension, it becomes pretty easy. You can assign one direction as positive, one direction as negative, and then add up the forces using just positive and negative. And here's a small example. If you've got F1 up and F2 down, again, look at the lengths of this. F1 is bigger than F2. So when you add these two together as vectors, F2 counts as negative because it's pointing in the opposite direction as F1. So the net effect is that it's still upward because F1 is bigger than F2, but it's not quite as large. So the total overall force would be up. And which way is the box going to move? Well, it's going to move up because that's the direction of the net force. And it makes sense because if you have a strong person pushing it up and a wimpy person pushing it down, the box is going to move in the direction of the larger force. But again, mathematically what we're going to do that's really important is first find the net force using vector addition, and then figure out the acceleration of the box or of whatever object you have. Okay, so once you do know the net force, how do you figure out the acceleration and what type of motion is going to happen to your object? So let's save this slide for a class discussion, but what we'll be discussing is when does the acceleration happen, for how long does it happen, and what happens before and after the acceleration. Is the object moving? Is it not moving? Is it speeding up? Is it slowing down? Let's talk about the dynamics of that in class. Okay, so there's going to be three Newton's laws, which you've probably learned back in 8th grade, but a lot of you might have forgotten, so we're going to review them again and maybe go into a little bit more detail. Newton's first law is as follows. It asks you to think about what happens to an object when there's no net force. That means the overall force is zero. That could be because there are no forces acting on it, or it could be because the forces acting on it all balance out. So if there's a 10 Newton force to the left, and there's also a 10 Newton force to the right, we would say these are balanced forces, and overall the net force is zero, even though there are still forces acting on it. So if the net force is zero, what happens to the object? Well, it turns out that if the net force is zero, the acceleration is zero, which means the object will not have an acceleration. It doesn't mean the object's not moving, it just means it's not accelerating. So remember, an acceleration is a change in velocity. So that means the velocity is not changing. So if it's at rest, it's going to stay at rest, but if it's already moving with some velocity, and the velocity doesn't change, then that means it's going to keep moving. So back in 8th grade, they probably had you memorize this sentence: an object in motion will stay in motion unless acted upon by an outside force. So that's the English sentence which represents this mathematical relationship. If the net force is zero, the acceleration is zero. And there's this key word that we use to describe the situation, which is called equilibrium. So if everything is in equilibrium, it doesn't mean it's not moving, it just means it's not accelerating because the net force is zero. Okay? So that's what happens if the net force balances out and is zero. But what happens if the net force is not zero? There's unbalanced forces. One force is larger than the other, or there's three that don't completely cancel each other out. Well, I think it's obvious the object is going to move, but how is it going to move? So there's a couple things that we have to take into consideration. Number one is the direction, and number two is the speeding up or slowing down of the object. So since the net force is not zero, the acceleration will not be zero. If the acceleration is not zero, that means the object must be speeding up or it must be slowing down, and that's going to depend on the direction. Or actually, there's a third option. It could be going at the same speed but changing direction, because remember that velocity is a vector. So a change in velocity could be speeding up, it could be slowing down, or it could be changing direction. Alright, so here's the equation, most important equation of the second semester, which is why it's got such a large box. You should probably, write this down on your hand, memorize it, sing it in the shower, do whatever you have to do to make sure that starting in about 10 seconds from now until you finish this class, you never ever forget that Fnet equals ma. The overall force on the object equals its mass times its acceleration. What that means is For a given size of force, if the mass is very small, the acceleration will be very large. Okay, so if you hit something little, it's going to go fast. If the mass is big, then the acceleration will be small. So if you hit a big object, it'll move, but only a little bit. And I think that matches your daily intuition. When there's a net force on something, it will accelerate, which means speed up or slow down. If you hit it the same way it's already going, it will speed up. If you hit it the opposite direction that it's going, it will slow down. And if you hit it perpendicular to its motion, it won't speed up or slow down, but it will change direction. It will veer off to the direction that you hit it. So it could speed up, could slow down, could change direction. All three of those represent a change in velocity, aka acceleration. All right, Newton's third law. This one has to do with the fact that forces come in pairs, okay? So we know that one object is going to move when you hit it, but anytime there's a force on one object, there's always an equal and opposite force back on the other object in that interaction pair. Here's a nice picture of Mr. David Beckham kicking a soccer ball. So when he kicks the soccer ball, obviously there's a force on the ball and the ball accelerates forward. What happens to his foot? Okay, the force from his foot on the ball is, say, in this picture, to the right. Therefore, the force from the ball on his foot is going to be to the left. So what that means is his foot experiences a force to the left. But you know his foot doesn't actually move left. But what does happen to it? It's coming in with some velocity. If there's a force backwards on it to the left, it's going to slow it down. So his foot is still moving right, but it's going to be moving slower over here than it was over here because of that backward force from the ball. And so it's easy to get these ideas mixed up where you think, oh, if there's a force to the left, the object must be moving left, but that's not the case. If there's a force to the left, the object will be accelerating to the left, but it might still be moving to the right, just slowing down. So there's lots of examples where the direction of motion is not the same as the direction of the net force, and then that just means the object will be slowing down. Okay, the mathematical representation is f of a on b equals negative f of b on a. Again, the negative, since it's a vector, the negative only tells you direction, so it's saying that the force of a on b is in the opposite direction, but equal size to the force of b on a. And then the sentence that you would learn is, for each force there's an equal and opposite force. Fantastic. Alright, so what have we learned in this chapter, chapter 4 on forces? There's quite a bit actually of content here, so we're going to go through it. We'll spend a lot of time making sure that you're masters of force diagrams, masters of this equations F net equals ma and force of gravity equals mg. So force of gravity equals mg is absolutely critical. Remembering again that this g is the same as it was in chapter 3. It's the acceleration on Earth's surface, or the force caused by the gravity of Earth, and it is 9.8. Units are meters per second squared. That's equivalent to newtons per kilogram. The units are equivalent. In fact, I'm going to write that down. Okay, that is identical to that. Same thing. So meters per second squared mathematically are equal to newtons per kilogram. So if you're looking at acceleration, meters per second squared makes more sense to use. If you're looking at forces, then if you're looking at forces, then newtons per kilogram. How much force are you getting per mass makes more sense. So the heavier the object is, obviously the bigger the force is going to be. Newton's first law summary: if the net force is 0, then the acceleration is 0. So that means no change in speed. It doesn't mean you're not moving. It just means there's no change in your speed. So there's no change. This is really, really, really important. No change. If the net force is not 0, then of course you're accelerating. So there is change. So it's not about moving or not moving. It's about a change in motion. A change in motion. This one we just did. Forces are equal and opposite. Force of gravity equals mg. Absolutely critical, just as critical as this one. So you should memorize both of these. And don't get them mixed up, actually. This is something I didn't realize was a problem until last year. The force of gravity equals mg is only for the force of gravity, not F net, not acceleration. This is just a force of things being pulled down towards the center of the Earth. And F net is the vector sum of all the forces, and that's what determines the acceleration. Okay? F net, yeah, that's what I just said. F net is the vector sum, so you have to add up all the forces as vectors, and that's what determines the acceleration. And then F normal is another force that we talked about. F normal is the force that prevents two objects from kind of passing through each other. So anytime two things are in contact, there's a force perpendicular to the surface which prevents them from going through each other, and that will typically be equal and opposite to whatever the force is that's pushing them together. For fun little example at the very end, we'll do this in class actually. So be thinking about, while you're watching this video at home or in class, be thinking about what it takes to win tug of war. Is tug of war won by how hard you pull, or is there something else that's even more important? And be thinking about the net force on these guys. Like, okay, let's draw a little Smurf guy. The net force on this guy, okay? You've got the force of gravity downward, okay? You've got the normal force holding him up so he doesn't sink into the ground, obviously. It's not, oopsie. Okay, now, he's pulling on the rope this way. So what is the rope doing to him? Okay, the rope is actually pulling him that way, right? Opposite of what he's doing to the rope. Okay, so, you know, all these Smurfs, they're getting pulled towards the left. What allows them to not go left? I want you to think about, I mean, obviously there has to be some force this way if they're going to win. So what is that force? I want you guys to think about that, and then when we come back to class, we'll talk about it. So, and also, yeah, of course, your homework is in the handouts, and you should start reading Chapter 5 in preparation for next week. All right, I hope this has been helpful, and we will discuss these things in more detail in class.